Hi, I'm Shahnawaz. Let us begin this lecture with the following example, which shows that linear independence in a vector space is intimately related related to direct sums of subspaces. Let us consider a vector space V over a field F. Now let us forget the scalar multiplication structure of V. Let us view V as merely an additive abelian group. Let X be the set of linearly independent vectors, say v1, v2 through vn. Let this be the set of linearly independent vectors and V. So we claim that V is direct sum of v1 through vn. This vi this is actually a one-dimensional subspace of V, and it is given to be, this is R times this little vi, where this R is in the field F. So this is a one-dimensional subspace which is spanned by this vector vi. Now by definition of these vectors, each vi each vector, suppose each vector v in V, this is big V, this has a unique expression of the form, has a unique expression of a form. So this V can be expressed as a1 v1 plus so on plus a n vn, where this ai vi, where this ai vi belongs to this little vi subspace generated by this vi. So this uniqueness and this expression over here, it proves that V is direct sum of these subspaces, one-dimensional subspaces. Thus V is direct sum of v1 plus through plus vn. Now conversely, suppose if X be a list of vectors, be a set of vectors in V is a set of vectors in V, which spans a subspace that is direct sum of one-dimensional subspaces, which spans a subspace of V which is a direct sum of one-dimensional subspaces. that is v1 plus so on plus vn. Now what we have to prove? We have to prove these vi's are linearly independent. Now let us consider a linear combination. Suppose sigma ai vi. Suppose this sum is in this subspace. So that this sum over here, this is 0. Now if this is 0, this implies, now note that this sum over here, this is a1 v1 plus so on plus an vn, so this is 0. Now also 0 plus so on plus 0 is also 0, so 0 is an element in this subspace which have two expressions of this form. But knowing that each element here can be uniquely expressed as sum of elements of corresponding vi's, one can note that these two expressions are equal. Now on comparing these two expressions, we get so we see that ai vi is 0 for all I. Now this product is 0 in the vector space, and this product is 0 in vector space if and only if either ai is 0 vi or vi is 0. But ai vi is equal to 0 holds in a vector space if and only if either ai is 0 or vi is 0. So this proves that, this implies that ai is 0. And hence this implies ai is 0 for all I, hence these vi's, they are linearly independent. Now one can note here that, let us make this an example, another example. So one can note here that if s1 s2, so let us make this remark. If s1 s2 through Sn are subgroups of an abelian group G, then we know that the subgroup generated by these Si's is the direct sum of these si's if and only if I pick any si and take its intersection with remaining si's, so this should be singleton. 0. Here the converse is not true, that is, if S1, S2, Sn are subgroups of an abelian group G such that intersection of each Si with the remaining sum of remaining Si's is a singleton set 0, then this subgroup here need not be equal to the direct sum of these Si's. Let us consider an example to support this argument. So let V be a two-dimensional vector space. Let V be a two-dimensional vector space over a field F, over a field F. Now again let us view this vector space V as merely an additive abelian subgroup, and let us forget the scalar multiplication in V. So let us consider, let X and Y let this set be a basis of V over F. Now let this be a basis of V as a group, be a basis. Now one can see that, one can note that the subspace generated by X, subspace generated by Y, and a subspace generated by their sum, they are all subspaces of G of dimension 1, are one-dimensional subspaces of V. So being one-dimensional subspaces, they are also subgroups of V. Now V has also an abelian group structure. So if we consider this subspace to be S1, this subspace to be S2, and this subspace to be S3, then note that this subgroup intersection this subgroup so this is nothing but this is 0. Similarly, comma X intersection X plus Y is again 0. and y intersection x plus y is again 0. This is again singleton 0. So this is true, but it does not imply but v is not equal to the direct sum of x plus direct sum of y plus direct sum of x plus y. This is not true. The reason being because if we consider this intersection, if we consider this intersection x plus y and take its intersection with x plus y, this is non-empty, so this cannot be direct sum. Had it been the direct sum, so this intersection would have been empty here, so this cannot be direct sum. So note henceforth note that if these SIs are subgroups and subgroups of an abelian group G, then this direct sum, then G is direct sum of then this group over here is direct sum of these SIs if this intersection is singleton, but this is not the other way around, i.e. if this intersection is the singleton, this subgroup here need not be the direct sum of these SIs. So let us prove the following proposition. So if G1 through Gn are abelian groups, and Hi, which is subset of Gi be subgroups of G are subgroups, that is G1 has H1 is a subgroup, H2 is a subgroup of G2, and similarly Hn is a subgroup of Gn, then we have the following isomorphism. The quotient of these two groups this is isomorphic to G1 mod H1 cross so on Gn mod Hn. Proof. Note that GIs are abelian groups and Hi being subgroups of abelian groups means that they are normal subgroups, so these quotient groups make sense. So let us define a map. Say phi from G1 cross so on cross Gn to G1 mod H1 cross so on Gn mod Hn. Now the identity in this group is, so this group contains n tuples, so the identity of this group and each component of each tuple is a coset, so the identity of this group is this tuple H1 through Hn. So this map is defined as phi sends an element and n tuple a1 through an to a1 plus h1, so on an plus hn. So we claim this is an isomorphism. Indeed, phi is a homomorphism. Since for a1 through an and b1 through bn and g1 cross so on cross gn, phi of a1 through an plus b1 through bn, so this is called phi of a1 plus b1 through an plus bn. So this is gonna map it to a1 plus b1 plus h1, so on an plus bn plus hn. So these are the cosets. So this is same as a1 plus h1 plus b1 plus h1, so on an plus hn plus bn plus hn. So this is same as a1 plus h1, so on an plus hn plus b1 plus hn, so on bn plus hn. So this is equal to phi of a1 through an plus phi of b1 through bn. So phi is a homomorphism. Indeed, phi is surjective by the definition of f. Clearly, phi is surjective. Now to prove phi is injective, we'll prove its kernel is singleton. Now kernel of this phi is all n tuples, say g1 through gn in g1 cross so on cross gn, such that phi of g1 through gn is the identity of the group on the right hand side, that is this n tuple. So this is h1 through hn. This is same as all n tuples in g1 cross so on cross gn, such that now phi of g1 through gn, it is g1 plus h1 so on gn plus hn. This is called h1 so on hn. Now these two n tuples are equal if they are equal component wise, that is if gi is equal to hi for all I. So this is all n tuples in this group such that gi gi plus hi is equal to hi. Now note that a plus h is h is if and only if an a is in h. So gi plus hi is hi if and only if gi is in hi. So this set is all g1 through gn and g1 cross so on cross gn such that gi belongs to hi. This is same as h1 cross so on cross hn. So this map is not injective, so we have computed this kernel. So by invoking first isomorphism theorem, we see that g1 cross so on cross gn mod kernel, which is h1 cross so on cross hn, is isomorphic to g1 mod h1 cross so on cross gn mod hn. So we are done.